Okay, so I had a request to do problem 4.24, so I'm going to work that out now. I don't prepare for these problems, I just look at them like right off the cuff so that you kind of see my thought process. So if I stumble through this problem, it's not because it is because I don't know what I'm doing. And hopefully that will help you learn because you'll see how I attack a problem. So I've never seen this problem before, and so let's just see if I can get through it. So 4.24, let's see. Consider the system shown in figure 4.45. So there's a control block diagram here, KP. So we've clearly got proportional integral control here, and then it hits the plant. So that is, let's see, it's first order, there's a pole at 0, it's a type 1 system, that's about it, marginally stable. Okay, and then it looks like the output is Y, they use capital Y because we're in the Laplace domain, and that's fed back. Okay, so pretty standard transfer function. So let's see, part A is compute the transfer function from R to E. Oh man, okay, that's kind of annoying. And determine the steady state error ESS for a unit step reference input signal and a unit ramp. Okay, so I haven't done this in class, so that's why my students requested to do this. So going from R to Y is simple because you just close the block and everything's all well and good. In order to get E, you have to do some things. So I'm going to call this C, and this is going to be CE, and then this, if I call this G, this is GCE, and everything's commutative, so you can just multiply everything together. So that means that Y is GCE, okay? And so those are all the transfer functions just multiplied together. Now, we want the transfer function of E over R equals question mark. So this is part A, and so in order to get E over R, I need an equation that has E and R in it and nothing else. So we gotta get rid of Y. Well, so if you look over here, right, this Y comes around here, this is Y, and then if you do, this summation block operation here, you basically get that E is equal to R minus Y. Okay, so then I need an equation with only R and Y in it, or sorry, R and E in it, so I need to substitute out Y. And so if I do Y really is R minus E, okay? Then I can just take a look at that and say, all right, let me just plug this into here and I'm gonna get R minus E equals GCE. And by the way, there's probably a formula in your book that just does this automatically, but I don't really like automatic formulas like that because I don't get an intuitive understanding of it. So that's why I just like to do it this way. So sometimes I just kind of like to read the control block diagram so I actually know what I'm doing. Anyway, so if I look at this, if I add this to the other side, I'm going to get R equals E plus GCE, and then R is going to be E, and I'm going to factor out a 1 plus CG. I moved the C and the G because I feel like I've seen this before. This looks pretty similar. And so if I divide by R and then divide by this side, I'm going to get E over R is 1 over 1 plus CG, which is, again, there's probably a formula in your book to do this, but I basically just derived it for you. I would say if you wanted to keep this in your back pocket and never do this derivation again, you're probably okay with that. I did assume that H was 1 though, so if you have an H in there, you need to completely rederive this equation here. But if H is 1, this is all good. If H is not 1, you just have to rederive this equation here. So now I've got a formula here, so that means I just do E over R equals 1 over 1 plus C, which is, let's see, Kp plus Ki over S, and then G, which is K over S. And then I need to multiply, I think, by S squared to get rid of the S's down here. So I'm going to multiply by S squared in the numerator and the denominator. So I'm going to get a numerator S squared. And then in the denominator, I'm going to get an S squared over here, plus, and then this is where things get complicated. So I'm going to get a kpk over s times s squared. So that's a kpk over s times s squared. The s squared cancels with the s, so I'm just going to get a kpks. Then I'm going to get a kik over s squared times s squared. So I'm just going to get a kpki. And that is my... I wonder if you can hear the helicopter flying over me? I feel like if I can hear it, you can hear it. Anyway, so this is r over e. And there is my transfer function, okay? So then the question is determine the steady state error for a unit step reference input. And so there are two ways to solve this problem. They asked you to get this transfer function, so okay, yay, like here's the transfer function, but you don't really need to do that to answer this problem. So the thing is like this is a type 1, right? But what is this? Well, this is a type 1 as well, okay? And so that means if you multiply these together, that means the entire system is a type 2, okay? So if I have a type 2 system, I automatically could just go to the table, and I know that for a type 2 system, right, all I need to do is go back to the table, and I feel like I should just always have this written down, but you know what? I don't. So I gotta flip back. Do I memorize it? No. Why? Because people have textbooks for a reason. Okay, so it says here that for a type 2, a step has an ESS of 0, okay? And then for a ramp, we have a ESS of 0. And then a parabola, these are inputs, by the way, these are the inputs. The ESS is a constant, okay? And so I can use the table and I'm done. I know I have a type 2 system. I didn't even need to do this. But there's another way you can figure this out. If R is a step, right, and you multiply... Did I do this backwards? I feel like I did this backwards. Let's see. I wanted E over R. Oh, okay. Wait, no, I had E over R. Did I just copy it down? I just copied it down. So E over R. I don't have my students here to like correct me. Okay, so if I do E over R, so if R is a step and you multiply this over, E is going to be S over S squared plus KP KS plus KP, right? And if you plug in S equals 0, E is 0. So that means the final value is 0. Remember, the final value theorem is you just plug in S equals 0. Okay? If R is a ramp, right, R over 1S squared, I'm going to get rid of my smiley face, I'm sorry. If you do R over 1S squared, then you're going to get E equals, the S squareds are going to cancel, you're going to get 1 over S squared plus KPKS plus KPKI. And if you plug in the final value, yeah, this is kind of odd. You plug in S equals 0, you get 1 over KPKI, but that's not right. Did I do something wrong? Because if you inverse Laplace this is going to go to 0. You know what I mean? So I feel like something's wrong with my final value theorem here. Oh, so the final value theorem only works if you hit it with a step, right? There are equations in the book for this, but you can only apply the final value theorem if R is a step, just because of the way the partial fractions work out. If you hit it with a ramp, you can't just plug in 0 and get the final value, because R is a ramp and the things don't shake out that way. What you do need to do is you need to do the inverse Laplace of this, and if you assume that these have two stable poles, like S1 is less than 0, S2 is less than 0, right? You have two stable poles. You know that you're going to get something that looks like E of t equals A e to the negative S1t plus B e to the negative S2t, and both of these are going to go to 0 as t goes to infinity. So it means that E is 0. The steady state is 0. If you do a parabola where you get 1 over S cubed, you're going to get an extra S in the denominator, which means you're going to get a constant term when you do the partial fractions. Cool? I'm actually going to upload separate... How long is this video so far? Let's see, 9 minutes. Yeah, I'm just going to upload 2 videos for this. This problem is kind of long. I'd like to get this to be kind of small. Well, actually, here, let me see how I can get into this. So, determine the location of the closed loop poles of the system, but they don't tell you what Kp and Ki are. So you can't necessarily do that, right? Because the closed loop, part B, right, it's the part B is the roots of this, but you don't know what Kp, Ki, or K are, right? Determine the location of the closed loop poles of the system. Well, it's the roots of, well, okay, I guess this is quadratic, right? So since it's quadratic, just use the quadratic formula, okay? Done. Okay, part B is done. Part C, select the system parameters such that the closed loop system has a damping coefficient of 0.707, omega n is 1, and what % overshoot would you expect in Y for a unit step input? Okay? Yeah, so I'm going to pause this, erase this. I'm going to take a picture of the board for the students who are in my class, and then I'll do part C. Okay?